Hello dear students. So, in continuation with our earlier discussions of single particle description of plasma, we have already seen that if the plasma is very weak or if the number of particles per unit volume in the plasma is very small, then we have understood that the collective behavior of plasma becomes unimportant, and then we can treat the plasma as a collection of single particles, each of them behave on its own. That means there are no interactions, or the interaction between the particles, between the individual particles is not very important. So, then what we do is, if this plasma is experiencing an electric or magnetic field or a combination of these, we can describe the plasma by saying or by analyzing the behavior of a single particle in the plasma, and then we can extrapolate this behavior or these equations of motion for the entire plasma. So, this approach was called as single particle description of plasma, where we treat plasma to be a collection of single particles. Okay. So, in our last discussion, we have seen how the plasma or how single particle will behave in a isolated, that means there is no magnetic field, isolated, homogeneous electric field. So, we have considered an electric field along z axis, and we have considered the movement of, let us say, electron and ion in these fields. So, what we have realized is that the velocity of the particle along the direction of electric field will vary linearly with respect to time. This is what we realized, and the velocity of the particle in other directions remains uninfluenced, right. In addition to this, we also realized the sum of the total energy, that is the sum of kinetic energy plus potential energy. The kinetic energy was a function of the mass of the particle and velocity of the particle. The potential energy is basically a function of charge of the particle and the electric field strength or the potential that is offered by the electric field will remain a constant. So, this is what we have learned. I mean, if a single particle is subjected to an electric field which is homogeneous in nature, that means it is not changing with respect to space, and static, that means it is not changing with respect to time, then in that case the total energy will remain a constant. A consequence of this is that the net work done will remain is 0. So, if there is no change in the energy, the work done is 0. That means what is doing this work? The work is done by the field, by the electric field. So, there is no amount of work that is done by the electric field. So, this is an important conclusion that we have derived in the last class. So, in continuation to this, what we will do today is that we will try to understand how a magnetic field will influence a plasma particle. So, this plasma particle's polarity could be positive as well as negative. That means, we can take an electron to be the particle which is experiencing a magnetic field. We can as well take an ion to be experiencing the magnetic field. Let us see how this mathematical approach will look like. Okay. Now, let us consider this case as case 2, which is uniform static magnetic field. So, this is the case in continuation. So, that means that uniform static and isolated magnetic field. So, how do you write it? So, in this description, the electric field is taken to be 0. The magnetic field is assumed to be constant with respect to time. So, there are no fluctuations. So, it is not a time varying field, it is a static field. It remains constant with respect to time. It also remains constant with respect to position, let us say. That means, it is homogeneous in space as well as in time. Okay. Now, let us consider a particle of charge q and mass m to be experiencing this particular field B. Now, from the generalized expression, the force that is experienced, the Lorentz force is written as q times E plus V cross B. V is the velocity vector, E is the electric field vector and B is the magnetic field vector. So, this expression reduces to F is equals to V cross B times Q. That means it will be, the force will be in a direction. So, if you consider V to be in one direction, velocity to be in one direction and the magnetic field to be in one direction, the force will be in a direction which is perpendicular to both velocity as well as the magnetic field, to both these. Okay. Now, what is the consequence of this? The consequence of this is the work done. What should be the work done in this picture? Work done is 0. Why? So, work done is, so how do you define work done? Work done as is the force times displacement. Now, velocity, that means if the force is perpendicular to V, it is perpendicular to the displacement as well. Since this force is perpendicular to the displacement, the work done will be 0. That means the effect of the magnetic field on the particle is such that it is having some effect. I mean, the magnetic field does influence the particle does experience some amount of force, but the net work done in this picture by the field is 0. Whatever the force that is imparted by the magnetic field is not doing any work as such. Okay. Now, how can we put it? Let us say we take again we take the rate of change of kinetic energy of the particle mv square, which is equals to qv dot v cross b. So, from the vector identities we can say that this is equals to 0. So, here what we can say is that number 1, work done is 0. So, we are saying this in the beginning itself. In the electric field case, we said this at the end of the discussion. So, work done is 0 and the second thing is energy is conserved. So, energy is conserved in this picture and the work done, the total amount of work done is 0. Now, what the scope of this discussion is to understand. So, if there is a magnetic field and if the magnetic field is not doing any work and it is not changing any energy of the particle, then what is the role of magnetic field? So, this discussion will be an effort to understand what is the role of magnetic field. How does it influence the particle? So, this is the idea. So, we have to understand by the means of simple mathematics, we will try to establish what is the role of magnetic field, what does the magnetic field do in this kind of a picture. Now, for this example, we will consider a magnetic field in this particular geometry. So, what we will do is, so we will consider, okay, so this is the coordinate system that we take, let us say x, y and z. So, the magnetic field is in this direction. So, this magnetic field is B z. So, the magnetic field is written as 0, 0, 1, or more easily we can simply write that, we can simply write the magnetic field as 0, 0, Bz. Okay. So, magnetic field has only one component. Now, we have to understand if a particle comes under the influence of this magnetic field, it can be an electron or it can be an ion, whatever it is. What will be the role of this magnetic field to change this particle's velocity or to change this particle's trajectory, so that at the end of this description we have the energy conserved and the net amount of work done as 0. Okay. So, this is the geometry of magnetic field that we take. So, in this example we can simply say that we can start from the general force expression. So, the force is m dV by dt is equals to q times v cross b. Now, the velocity of the particle, so this is the expression for the force. Velocity of the particle is in 3 components: Vx, Vy, Vz. Okay. Now, the velocity of the particle Vz is going to be called as V parallel. The reason is Vz is in the direction parallel to the magnetic field. Vx and Vy are going to be referred as V perpendicular because they are perpendicular to the magnetic field. Okay. Now, what we can do is we can resolve this. So, we have the magnetic field given as this and we have the velocity given as this. We can resolve this curl or cross product as I can write m dV by dt is equals to q times I into Vy Bz minus Vz By in the next line minus, so j cap, the unit vectors Vx Bz minus Vz Bx plus k cap Vx By minus Vy Bx. This is the full expansion of the cross product. Now, we substitute the actual field that we have got, then we will get what we will get m d by dt of I Vx plus j Vy plus k Vz is written as q times I Vy Bz minus j Vx Bz plus k cap into 0, right. So, this is a 3 component equation. So, we can write an equation for x component, y component and z component of velocity from this single equation, which will look like m dVx by dt is equals to q Vy b. Let us call this as equation A. Then m dVy by dt as minus q Vx b. Let us call this as equation B, and m dVz by dt is equals to 0. Let us call this as equation C. So, what we have done? What we have done is we have simply written this equation, the Lorentz force equation, into component form. So, we have now we get force along the x axis, force along the y axis and force along. So, this is this can be force along the x axis, this is the force along y axis and this is the force along z axis. So, before we go ahead, we can now itself we can say that force, now B is simply Bz anyway, B is Bz, right. So, force along x axis is coupled with the force along, with the velocity along the y axis. Similarly, force along the y axis is coupled with the velocity along the x axis, and force along the z axis is 0 because particle's velocity is parallel to the magnetic field because of the curl. So, it is parallel. So, the curl will make it as 0. So, what do we infer? We infer that we can break the Lorentz force expression into these three component equations, and these three component equations indicate that the force along the z axis is 0. Okay. Now, so let us say from equation B, we can write that d Vy by dt is minus q by m Vx B, which implies Vy is equals to minus q Vx B times t divided by m. Okay. Now, let us substitute this, let us say let us substitute this result, the Vy result, into Vx, which is given using, let us call this as equation D, using equation D in equation A. Okay. What we can write is m dVx by dt is equals to q times minus q Vx B times t by m into B, which is equals to d Vx by dt is equals to minus q square B square Vx t by m square, right. Now, if we differentiate this, we will get d square Vx by dt square is equals to minus q square B square Vx by m square, right. So, now what we have done is we have coupled, we have Vy, which we substituted into the expression for Vx. Similarly, we can substitute Vx into the expression for Vy, which is equation number B, and this was equation number A. Then we will get another second order differential equation, which is d square Vy by dt square is equals to minus q square B square Vy by m square. Okay, let us call this equation as E and this equation as F. Now, we already had one expression for dVz, and we can write d square, differentiating it again with respect to time, d square Vz by dt square as 0, and let us call this expression as G. Now, so by starting from the expression for the force q times V cross B, and from starting from there, getting the value of dVx by dt and differentiating this expression again, we have got three second order differential equations. What do they represent? They represent, what do they represent? They represent the trajectory of the particle's velocity. They simply represent the trajectory of particle's velocity. How does it look like? Okay. Now, so simple, I mean, we can say that this is a second order differential equation, and any harmonic solution for Vx or Vy will satisfy these equations. Okay. d square Vx by dt square as minus omega square Vx such that omega is written as QB by m. Similarly, d square Vy by dt square as minus omega square Vy and d square Vz by dt square as 0. So, what is the change? The change is that we are calling this QB by m, q square b square by m as omega square. So, in this expression, right. So, we have this expression in terms of d square Vx by dt square is equals to omega square Vx. Okay. Now, these equations look like they can take a simple harmonic solution, which we will write as Vx as, now we will write Vx as a cos omega t plus b sin omega t. Now, let us say if this is given as this, we can write dVx by dt as minus a omega sin omega t plus b omega cos omega t, and d square Vx by dt square is minus a omega square cos omega t minus b omega square sin omega t, which is simply d square Vx by dt square as minus omega square Vx. That means the choice of solutions we have taken holds for the given differential equation. Okay. Now, if it is the case, now there are, it is a second order differential equation and we have two constants. What are the constants? The constants are a and b. We need to find out the values of these two constants before we go ahead. Now, what are the values of these two constants? What can be the values of these two constants? So, in order to find the values of these two constants, we need some conditions. We need some initial conditions. Initial conditions. What are the conditions? Let us say at t is equals to 0, the velocity Vx is taken as V0x and the velocity Vy is taken as V0y. Okay. Now, what we can do to find out the values of these constants? We can substitute these conditions in Vx. Okay, let us see. Okay. So, let us say at t is equals to 0, in the beginning Vx is equals to a into 1 plus b into 0. That implies at t is equals to 0, Vx is V0x, that is equals to b. No, that is value of, so this is the value of b. So, by applying an initial condition, we got the value of V0x as b, or b is equals to V0x. Now, we already have dVx by dt, which is written as minus a sin omega t times omega plus b cos omega t times omega. And in addition to this, we have one equation which is m dVx by dt is equals to q times Vy b. This is from the original equation that we have. this equation was the product of cross product, resolving the cross product. So, if you see this, the d, so if you want to, so we have taken the v to be Vx, Vy and Vz, right. Now, we said Vz is not going to be influenced by the magnetic field, and Vz was called as V parallel, Vx and Vy were called as V perpendicular. Now, we have taken a solution for Vx in terms of constants, let us say A and B. We should also have a solution for Vy, which will also satisfy the second order differential equation, which is d square Vy by dt square, which is in terms of minus omega square Vy. In addition to this, now we get a relation which is in between Vx and Vy. So, now it gives us a possibility wherein we can get the value of Vy or get the functional dependence of Vy from Vx itself with the same, without involving two more constants. Okay. So, that means that if you use this, if you combine these two equations, what you can write is Qb by m Vy, Qb by m Vy, because dVx by dt is Qv Vy Vyb. So, now we have 1 m which comes here is omega times minus a sin omega t plus b cos omega t, right. Now, we know that Qb by m is omega. So, omega Vy is omega minus a sin omega t plus b cos omega t. We cancel omega and you can write Vy as minus a sin omega t plus b cos omega t, right. Now, where were we with respect to Vx? Vx is V0x cos omega t plus b sin omega t. Now, there is a small mistake. It is that, now if it is the case, now we need to find the value of b. The value of A was suitably substituted as V0x from applying the initial condition. Now, we need to find out the value of b. Now, similarly, let us say at the beginning, at t is equal to 0, Vy would have been V0y, right. Now, using this into this equation, into this equation, into this equation, we can write that V0y is equals to minus a times 0 plus b times 1, which implies b is equals to V0y, right. Now, we have both a and b. So, a is the initial velocity along the x axis and b is the initial velocity along the y axis for this kind of a solution, right. Now, we will simply have to substitute the values of a and b for getting the full functional form of Vx and Vy such that they satisfy this type of second order differential equation. Now, what is particular about this type of equation? They represent particle motion. They represent particle motion. Okay. So, we will continue this discussion in the next lecture, how we can interpret these two Vx and Vy and how they can tell us how the particle will move with respect to time in the presence of an external magnetic field. Okay, thank you.